Okay, in the last video we derive a relation between Cp and Cv, which is given here. Now we will apply this relation and find the specific heat at constant volume and at constant pressure for different gases, like heat capacity at constant volume, and constant pressure. We consider the case 1 first, and the case 1 is for monoatomic gas. Like oxygen, hydrogen, etc. Now we know that the change in internal energy delta E internal for at constant volume is NCV delta T. Or we can write CV is equal to change in internal energy delta E internal divided by N delta T. Now this is equation number 1, and we know that we already derived this for monoatomic gas. We derive a relation for the change in internal energy in the classroom, which is 3/2 nR delta T. This is, let's say, equation number 2. We already derived this relation in the classroom. So using equation 2 in 1, we have CV is equal to, instead of delta change in internal energy, I will put this relation 3/2 nR delta T over N delta T. N cancel with this, delta T cancel with delta T. So we have CV, which is 3/2 R. And the numerical value of CV will be 3/2, and the value of R is 8.314 joule per mole. Per Kelvin. So if we calculate this, we finally get CV is equal to 12.5 joule per mole per Kelvin. This is specific heat at constant volume for monoatomic gas. Now we have a relationship between CV and Cp. Cp minus Cv is equal to R. We have Cp is equal to R plus Cv, and we have Cp is equal to R plus Cv. We already derived this relation from monoatomic gas, which is 3/2 R. So instead of Cv, we will put 3/2 R. So from this we get the Cp, which is 5/2 R, 5/2, and the value of R is 8.314 joule per mole per Kelvin. If we simplify this, we get the specific heat at constant pressure for monoatomic gas is 20.8 joule per mole per Kelvin. This is the value of Cp, and we have the value of Cv, which is here, which is 12.5 joule per mole per Kelvin. Next we will consider the case of diatomic molecule. Now again we have the same relationship, which I don't want to repeat it again. Delta change in internal energy is 5 divided by 2 nr delta T, and also this is we have the relation for the change in internal energy delta E internal, which is NCV delta T. And for diatomic molecule, we also derive a relation like this in the classroom, which is 5 divided by 2 nr delta T. Now comparing these two equations, we get NCV delta T is equal to 5 divided by 2 nr delta T. Delta T cancel with delta T, n cancel with n. So we have CV, which is 5 divided by 2 r. And if we put the value of r, 5 divided by 2, and the value of r is 8.314 joule per mole per Kelvin. And if we simplify it, we get CV is equal to 20.8 joule per mole per Kelvin. Now again we have CP minus CV is equal to R. From this, CP is equal to R plus CV. R plus CV is this one, 5 divided by 2R for diatomic gas. From this we get 7 divided by 2R. And if we put the value of R here, 7 divided by 2, and the value of R is 8.314 joule per mole per Kelvin, we get the final expression is CP for CP is 29.1 joule per mole per Kelvin. So we also calculate the value of specific heat at constant volume and at constant pressure for diatomic gases. And next we will consider the case of monoatomic gas. Now for monoatomic gas, the third case, which is monoatomic gas. Now we have this relation for the internal energy, change in internal energy, which is NCV delta T, and for monoatomic gas, for polyatomic, sorry, not mono, this is for the polyatomic gas. For polyatomic gas, we also derive a relation in the classroom. The change in internal energy is 3 nRT delta T. Now comparing these two equations, we get NCV delta T is equal to 3 nR delta T. N cancel with N, delta T cancel with delta T. Okay, in the next video we will proceed forward.